He worked on several legislative issues related to aerospace and telecommunication policy, including the anti-spam legislation. So he's the one we blame for all the spam that we get. Professor Hajela is a fellow of American Institute of Aeronautics and Astronautics, a fellow of the Aeronautical Society of India, a fellow of American Society of Mechanical Engineers, and the vice president of the International Society of Structural and Multidisciplinary Organizations. He has held many editorial assignments, including editor of Evolutionary Optimization, associate editor of the AIAA Journal, and is on the editorial board of 6 other international journals. He has published over 260 papers and articles in the area of structural and multidisciplinary optimization, and is an author or co-author of 4 books in these areas. In 2004, he was the recipient of AIA's biennial Multidisciplinary Design Optimization Awards. Ladies and gentlemen, I give you Professor Prabhat Hajela.
The subject of soft computing, I guess, to a large extent was introduced this afternoon by Vishal Sahni and Satish Kumar. So it has made my job a lot easier today. I mean, I'll be able to rush through a few of those slides without having to go into details. But what I'm going to be talking about primarily today is the adaptation of soft computing methods in a problem, in a specific problem. That problem is system analysis and design. So before I get into that, let me tell you some characteristics of the system analysis and design problem first. We'll start with an example. Here's a helicopter rotor blade. This is the design of this blade. Requires interactions between disciplines like structural design, aerodynamics, control systems. You see that I've represented in this cartoon sketch each of these disciplines by these 3 circles, but there is a great deal of overlap or interaction or coupling that exists between these subsystems. The analysis that is involved is computationally intense and in many instances is incompletely defined. You must resort to experiments to get certain amount of information back that could be used in the design process. Similarly, here's an example of MEMS systems. Here's a 19-tooth gear and linkage arm of a micro engine. Here's a mirror mechanism laid out against a spider mite to show the dimension of this. But in effect, because of these dimensions, disciplines like electrostatics must be considered in addition to material science, manufacturing, stress analysis, and thermal effects in the design of systems like this. Once again, it's a coupled analysis. It is computationally intense. And in many instances, you have to resort to experiments to try and get analytical data in order to perform the design itself. A third example, you have to include effects of manufacturing in the design process. So here you see an automated composite layup machine in which you have a robot arm which lays out fibers, composite fibers over a mold at specific angles. Here's this curved panel in which you are cutting out certain objects, again by an electronically controlled machine. The issue here is that we would like to migrate the manufacturing process as early in the design process as possible. And in order to do that, you must have models which represent the manufacturing process itself. Here's a more detailed representation of that. Here's that curved panel. I have put some cutouts here. These cutouts might have to be placed because this panel is covering a cavity which you might have to access for maintenance purposes. So here's your fiber layup machine. It has to control the panel thickness, the geometry of the panel, the curvature, as well as the location of the cutouts. And the goals of designing this might be, you might want to minimize the layup time that is required to build this panel. You want to certainly minimize the material cost. Of course, you want to guarantee structural integrity of this part, and then place these cutouts in such a place that you can actually maintain this object that you are trying to cover with this panel. So the goal of this is you must be able to represent all of your design goals in terms of certain mathematical variables, as well as be able to include nuances that are related to the manufacturing process. Not all manufacturing processes can be modeled exactly. You sometimes have to go to the shop floor to get feedback from the operators on when a machine functions well, when it fails, and be able to model that into an appropriate mathematical format that can be then used by your standard design algorithms, which might be your classical mathematical programming algorithms or soft computing algorithms that were discussed earlier this afternoon. So, in summary then, the system analysis and optimization problem that we'll talk about here has these characteristics. The final product or system is generally an integration of several distinct subsystems. There are design parameters and constraints in each one of these subdisciplines, and the overall desired objectives are essentially met by varying the parameters within each subsystem. Collectively, for all of the subsystems, the number of design variables and constraints may be quite large. And also, you cannot, in most cases, conduct design in isolation because changes in design parameters that take place in one discipline have an adverse or beneficial effect in another subsystem. So you have to take those coupling accounts into effect as you go through the design process. At the heart of all of this is the design optimization problem, which is mathematically stated as follows. I mean, all of you who have dealt with optimization have seen the structure. You're minimizing a function which could be a vector quantity or a scalar quantity subject to a set of inequality or equality constraints as well as side constraints on the design variables. These design variables can be a mix of either continuous variables, discrete variables, or integer variables, and you may have a large number of such variables. Now, pay close attention to the fact that there are discrete and integer variables because soft computing techniques really come to our aid in this particular instance. The design space may be non-convex or disjointed, and I'll just show you a sketch of what I mean by that. And your traditional optimization methods are ill-equipped to handle this kind of a characteristic in the design space. You also have to deal with non-crisp design information, and the speaker this afternoon, Dr. Kumar, talked about fuzzy modeling as a way to get around this, and I'll also have an example to show you where this has been used. This quickly is an illustration of a non-convex space, classical function with 4 local optima. In this case, each one of these 4 local optima have the same objective function value. You know your traditional gradient-based techniques will converge to the nearest local optimum from where you start. Here is an example of a disjointed design space where you have regions of feasibility separated by large regions of infeasibility. So when you get into one of these feasible spaces, it's unlikely that you're going to get out of them using your traditional gradient-based mathematical programming algorithms. So what are the soft computing adaptations that I will talk about here today? Neural networks and fuzzy logic. Dr. Kumar talked about surrogate modeling of the analysis. That's certainly one application that we have used extensively. Discovering causality in data becomes important as well, because if you have a large optimization problem involving a very large number of variables, you want to perhaps break it down into a sequence of smaller, albeit coupled problems. You would like to find out which variables affect which design constraints so as to make a rational choice for that decomposition. Again, artificial neural networks have been used in that process as well. Genetic algorithms certainly have been very useful in designing non-convex and disjoint problems, as well as topology and layout type of problems. And when you talk about nano-assembly, for example, which are topological problems, genetic algorithms have a significant role in that regard as well. I'll talk a little bit about immune network modeling. This is a variant of genetic search, which I'll show how it has been used in problems of constraint handling, as well as in accounting for the interactions in decomposition-based design. And finally, I'll say a few words about cellular automata and the implications of this particular computational paradigm in both system analysis and design problems. So I don't have to dwell too much on this chart. Again, Dr. Kumar talked about this. Function approximation is an area in which neural networks have been used. I'll talk a little bit more extensively about determining topology of decomposition. They have also been used as optimization tools. I mean, the classical Hopfield network, for example, if you create the variational just right, you can actually get a solution to NP-complete problems, and those works have been published in the literature. But as someone was saying this morning, that's a niche type of an application. It is not so easy to construct the appropriate functional to be able to do that. There are two specific architectures, the backpropagation network and the counter-propagation network, that we will discuss here. This is your backpropagation network, and again, I'll not dwell on this in the interest of time. Dr. Kumar already spoke to this subject. The one thing that I will say is that this is very much like a response surface. You have a set of input-output data, and in effect, rather than training the coefficients of those polynomials in a response surface, you are in essence finding out what are the interconnection weights and the characteristics of your neural network, or of your artificial neuron, that give you the best match between the input and output. These are the characteristics. Certainly these can learn to modify behavior in response to the environment, as well as they have the capability of generalizing. So if you present input data that was not part of the original training set, you get an approximation to the output. That's what contributes to the function modeling capability of this particular architecture. They have also been used in other applications. I mean, certainly in control theory, they have been used extensively. Here's where real-time response is required, and there have been a number of successful applications of this technology in that area as well. The counter-propagation neural network is shown here. Again, you have a set of input. This particular architecture that I have shown here, the inputs x1 through x5 and outputs y1, y2 are essentially mapped by this Cohonen network into an identity mapping. All right, so I've created an identity mapping. The input-output is completely mapped into an input-output. The advantage of this being that if you, this particular network has the capability of pattern completion. So if some components of the input are actually missing, it can create an approximation to those on the external, on the output side as well. What does the Cohonen layer do? Cohonen layer essentially classifies the pattern into a, that it belongs to a certain cluster or category. And then on the outside, you have the outstars, which are essentially Grossberg generalization neurons. They take the output of the Cohonen neurons and give you, by combining appropriately the contributions from the different neurons, if you're using some kind of a nonlinear averaging, it gives you an appropriate output. So some characteristics of this network, they go beyond the representational limits that are available in a single layer network. When compared with backpropagation, they train a lot faster. I have already stated that they are a combination of the self-organizing Cohonen as well as the Grossberg classifiers. They function as lookup tables capable of generalization, and to that extent are a better model of the biological brain than your backpropagation network. This point is an important one to remember. The generalization capability actually allows the network to produce the correct output even when the input vector is partially incomplete. So there's a pattern matching or a pattern completion capability. Again, it can be used very effectively as in a robust control environment, where if you have loss of certain sensor data, then the network actually makes up or constructs approximations to that and gets the job done safely. Okay, so I'm not going to dwell on that slide, just show you some examples. Here's a design problem in which we have a reinforced composite panel with some stringers. In case you're wondering why I keep talking about structures and materials, it's I'm an aerospace engineer by training, and this is what I feel most comfortable about, and hence I'm using these examples. But we are trying to design this panel, essentially getting things like the height of this reinforcing stringer, the crown width, the width at the base. This is built out of composite materials, so you have the thickness to control as well as the layup angles of these plies, composite plies that you're building. Here's your objective function. It is subject to a number of constraints, and in essence just wanted to show you that while you have a mix of discrete, continuous and integer variables, you can still use this this type of a problem in a neural network, a backpropagation neural network, to actually come up with things like predicting natural frequency, buckling load, the maximum deflection, maximum von Mises stress. And you can see that the maximum error that you pick up is maybe of the order of 6%. Most of them are 1 to 2%. So if you build a approximation using a neural network, it can be very effectively adapted and used in multidisciplinary design type of problems. It's essentially a free computation once you have a network trained, the computation is free, and when you're using it in conjunction, for example, with an evolutionary algorithm which requires a lot of calculations, this surrogate model is a cheap one and highly advantageous to use in those kinds of applications. Let's say a few words about discovering causality from trained backpropagation networks. If you were to simply take the weights of the trained network and multiply them in this sequence, that is the weights between the input layer and the first layer, between the first and the second layer, and so on till you get to the output, in essence what you get is something called a transition matrix. If you normalize that transition matrix by the operation shown here, which is essentially the maximum element in that particular row, you actually come up with a causality matrix which tells you what is the influence of a specific input component on an output. So here's a quick example to demonstrate what I'm talking about. What you see here is a 5-bar truss structure subjected to these two loads, P. What we did was we trained a neural network with some random data which said that if I chose the cross-sectional areas of these bars at random, A1 through A5 are the cross-sectional areas of these bars, what displacement do I get? D1, D2, D3, D4. I then trained this network and created a mapping between the areas and the displacements. I went through the process of forming the transition matrix T, and here's what it looks like. So you can see very clearly that the displacement D1 is most strongly influenced by the area A1, as you should expect. That's the axial resistance that you are getting from that particular component. Likewise, D3 is component 2, area 2. D4 is most closely linked to 5 and 4. You would expect that maybe 5 should contribute to this as well, but it doesn't, and there's a very good reason for it. In fact, if you look at this entire last column, none of these numbers are large enough. If you do a closed form analysis of the areas and displacements, you find that this bar does not play at all in the displacements D1 through D4 because of the particular loading pattern that you see. 2 equal loads on each side. It's essentially a scissor type of motion that you are getting from this truss. So it's an unloaded member. This is very useful in trying to determine then that if I were designing just for displacement D2, then I know that the area A3 is the most critical one, and I would use that, the design variable, which is dominant in displacement D3. And this brings me to the subject of decomposition-based design. When you have very large number of design variables and constraints, pruning the design space of ineffective design variables and or constraints is an important consideration. So you decompose the problem into smaller, either disconnected or weakly coupled subproblems. What you need is a rational approach to partition these subproblems, as well as an approach to account for these subproblem interactions. You saw in the previous chart that although this is the dominant influence, you still have some influence left here. Or in this case, there is some influence of these other variables as well. So can you use that information appropriately when you are trying to retain or account for the subproblem interactions? People have resorted to things like heuristics to do this. Machine learning has also been put to test in these kinds of problems. But let's just illustrate this with another example. This is the same rotor blade that we talked about. Various design variables defining the plan form of this blade, as well as the internal dimensions of the cross-section of the blade, which look like an airfoil. Again, you see that it's a mix of continuous, integer, and discrete variables. Fairly large dimensionality problem. We created a neural network, and what you find is that you can actually split the variables up into the form shown here, that there are 3 subsystems. You have consolidated the constraints and the design variables into 3 groups, and these 3 problems could be solved simultaneously if you knew how to account for the interactions between these 3 decoupled subproblems. Again, this partitioning has been done on the basis of that same causality matrix that we talked about earlier. Much larger causality matrix, but it gives you some idea of how to partition the variables. It's rather interesting to note that the masses, this blade has actually tuning masses, which are masses that are placed along the rotor blade, which take care of the vibrations in the blade, right? how much to place and where to place them are design variables in this problem. But it's interesting to see that in subsystem A, masses M1, M2, M3, which are three masses closer to the root, fall into subsystem A. Subsystem B does not contain any of those masses, and M4 and M5 actually go into subsystem C. So in a typical industry type of design environment where people are constantly fighting about control of design parameters, this kind of an approach gives you some leeway as to how to partition the design space and say, you folks essentially control these variables. The variables that belong to another subsystem actually impact their design problem far more importantly, therefore it should go there. Counter-propagation networks, similarly, as I had shown earlier, could be used for approximations, and this is that same problem, this one particular problem, where I'm mapping the forces at the root, forces and moments at the root of the blade in terms of the design variables, and you can see again that you get fairly good degree of approximation, so the CPN could also be used as a function approximation tool. Quickly turning our attention to the next paradigm, fuzzy logic based modeling. Again, Dr. Kumar spoke of this earlier, but what we mean by this is that you would, for a typical designer, it is sometimes important to keep that fuzzy information in the design problem. When you convert it into a crisp form, you sometimes lose the original intent of the problem statement. Stating it in this fuzzy form allows a smooth transition between the two bounds. So for example, here if you're saying that the structure is required to withstand a stress of about 20,000 psi, and you admit a 10% relaxation in this, then the membership function might look something like that. Right? Here is a fuzzy logic, the membership function for height. Again, this is something that Dr. Kumar alluded to earlier in his presentation, so I shouldn't have to spend time here. Important thing here again is that fuzzy logic rules use essentially conditional statements. These are if-then rules. For example, the fuzzy if-then rule could assume the form that if x is a and then y is b, where a and b are both linguistic variables. Where this has been used, here's a quick example. Manufacturing of composite panels, this could be laid up by hand, which is a labor-intensive process, or you could resort to an automated fiber layup machine. You can get both time-saving, less scrap, as well as precision if you were to use this machine. And there's a machine manufactured by Cincinnati Millicron, which is called an automated fiber placement machine. You essentially build a mold of a part, and then the machine can traverse at various angles, at various speeds. It can compact the fiber as it lays it down. All of those wonderful things it can do. But in theory, while that works fine, if you go to the manufacturing floor and talk to the people who use that part, they will tell you that there are some problems with it. So the layup time that we are talking about here, it depends on the maximum feed rate. How quickly can this part move back and forth? It depends on the part geometry, as well as the direction of the head movement. So all of these design parameters which also affect the structural integrity of the part, because the fiber angle will tell you how stiff the panel is, right? The thickness will tell you how stiff the panel is. The curvature of the panel tells you how functional the panel is. All of those are in fact also dependent upon the manufacturing considerations, because this machine, the layup time that you're talking about, may or may not be optimized depending on that. So you would like to include those manufacturing considerations in the design process. Any delay that is encountered in the manufacturing process we refer to as a downtime. For example, the operator has to stop the machine and then manually steer it in a particular direction, or has to replace a compaction roller. If the radius of curvature of the panel is too small, then you have to put in a smaller roller, otherwise the fibers will form a bridge between the two sides. So all of these things require careful monitoring in the design process. You could use fuzzy logic in effect to incorporate the operator's knowledge. So this we did as a DARPA funded project with Boeing. We went in and talked to the operators who were using this machine. They told us that, for radius of curvature typically less than 60 inches, the machine has to be slowed down and manually steered. Okay, so here's one piece of nugget. The speed of the machine needs to be reduced as the radius of curvature decreases, because otherwise you get longer downtimes. For radius of curvature close to 5 inches or less, the roller should be replaced with a lower bandwidth roller. Again, you see that there is fuzzy information being transmitted. Minimum allowable radius of curvature is about 1 inch. Again, fuzzy information. And the corresponding downtime is approximately 1 hour. So you get all of this information feedback from the designer, and you essentially could then go ahead and say that, all right, I'm just going to create 3 sets of rules. If the radius is small, then the downtime is long. If radius is medium, then downtime is average. If radius is large, then downtime is short, based on all of those rules. And here are the input-output membership functions. Here is the kind of a model that we produce, that the downtime based on the radius of curvature is represented by that simple chart. Now, once we have that model, this could be brought back into the design process and be part of the mathematical optimization or genetic algorithm or any other algorithm that you want to use to solve that optimization problem. But you now have a mathematical representation of the problem that you could use as part of the design. So this brings me then to the subject of genetic algorithms and evolutionary strategies. These are certainly algorithms that are patterned after natural evolution. They are population based. That's the critical thing to remember. There are some advantages to having a population based search. There are also disadvantages. You essentially start out by taking your designs and mapping them into string-like structures, and then apply typical evolutionary operators such as crossover, mutation, selection, and so on that you encounter in biological principles of evolution. It's very easy to represent and handle discrete variables and templates in this type of design algorithm-based approach. There is no requirement of sensitivity information or function continuity. So 2 things that I spoke about earlier: disjoint design space and computational cost. Getting function information is one thing, getting the gradients of those functions is even a harder level problem. So if you can avoid getting gradients and have an optimizer that helps you get to the solution, that is a plus in your favor. This is just a cartoon sketch which shows what we are talking about here. Population of seals, they probably have a gene pool that looks like this. Subject to certain environmental input, these genes evolve to give these critters here the maximum chances of survival on the, as they're resting on the beach. Here's a design of missile systems. You might have geometry, you might have structural casing that you're trying to build for these particular missile systems. You take those design variables and represent them by binary strings in this case. You could also use real variable representations, that's not an issue at all. And then the environmental input in that case becomes your fitness measure to what must this design evolve to be considered fit. And you then subject these strings to the kinds of evolutionary operators that I just described. So here's your genetic algorithms in one chart. Here's the representation in string-like structures. You have a function that you're trying to minimize that gives you the fitness value. You could select a particular string based on its fitness. You could select members to crossover. So simple crossover might be, here's a string yellow and a string red. You've selected a site, you simply swap the genetic information between the two to create 2 offsprings. Mutation would be to select a site on this string and just flip it at random from a 0 to a 1, or otherwise this population pool is subjected to evolutionary pressures, and in effect generally what you get to see is a convergence that looks like this. So here is an optimized design, here's the best value that you can get for the fitness. The entire population then works its way up and you get an asymptotic approach to that maximum fitness value. Now, because of the fact that this is a population-based search, genetic algorithms offer you this advantage, this extra little bit of caviar, that if you have a problem with multiple relative optima, you could converge subset of those populations around each one of those local optima as well. So in a single GA search, you could identify multiple relative optima, giving the designer then the ability to actually decide for themselves which design they would like to go with as far as the manufacturing is concerned. Okay, so these are the simultaneous searching from various regions of the design space. You have many members of the population. Information from all sides of the design space is actually brought to bear to go to the next step. That's what gives it the higher probability of actually finding the global optimum. They are very well suited for parallel computers, and both coarse-grained as well as fine-grained parallel models have been introduced. They can be adapted for large number of design variables, but here again, in order to do that, sort of a decomposition-based approach is proposed. Dr. Kumar started to talk about it earlier this morning, that you might have actually coevolution that you might want to consider, and I'll say a few words about that as well in this talk. But just remember that all of these advantages come at a significantly increased computational cost. That's the downside of genetic algorithms, that for each generation of evolution, it's not a single design that you evaluate, but multiple designs. So linking it with function approximation tools becomes an important approach. I think it's worthwhile to say a few words about constraint handling in genetic algorithms. I thought that this was something that people need to keep in mind. Typically, if you have a function that you're trying to maximize, you could simply use that as an objective function, right? When you're trying to minimize subject to some constraints, then what you do is you take the constraint violation and lump it onto the objective in the form of a penalty, right? So once you have a penalty function and you minimize that function, minimizing that penalty will actually drive it to 0. How is that penalty function created? Well, you say that I'm simply going to take it as a sum of the values of those constraints if they are violated, along with some parameter r, as long as this g is less than some limiting value. If that limiting value is exceeded, then I allow the p bar to grow above that by a small quantity that is given here linearly. The problem with this, of course, is that there are a number of different parameters that you must select. L bar, alpha, r, all of these are parameters that the user selects. And then the algorithm becomes sensitive to the choice of these parameters as well. So an alternative approach that has been proposed is something called an expression-based method. What the expression-based method does is borrows from the principles of biology, where in fact you have in biological systems, your chromosome is actually a double-stranded helix structure. It's a diploid structure. There are 2 chromosomes. At each site, it's an expressed gene that comes from the two strands of this chromosome that decides the characteristics. And dominant recessive gene theory is used to actually determine what characteristic is expressed. In a traditional GA-based search, the designs are represented by a single stranded structure. Remember, we just have a single strand of 1s and 0s, so that's the haploid structure. So could we actually borrow from this principle and say, let's combine the features of feasible and infeasible designs in a given population through the use of an expression operator, which is probabilistic in nature. The idea here is that, let's say that here's a string A which is feasible, string B which is infeasible. You temporarily assemble a diploid model, then you carry out an expression operator on a bit-by-bit basis to determine what gene is expressed at a particular point along this string length. And this is done with the probability of expression p sub e. So you reduce this down to a single parameter p sub e. This has been successfully implemented in genetic search, and actually is shown to be a much more robust way of handling design constraints than the penalty function approach. Okay, so what are some of the examples of genetic algorithms in system design? In topological layout problems, it's been a very important contributor. If you are given a problem where you say that there are these little nodes in the space, or let's say that you just have these this outside domain defined, some loads are applied and then support points are given. Let's try and find out what is the optimal topology of axial load members that will carry these loads, will be least weight and will give you the best performance. Depending on the geometry, you can see that this can be connected in a large number of ways, and selection of the connectivity is what makes for an optimization problem. So this is a discrete design variable problem. Here is in a system design type of a problem. Here's the stick model of a CH-47 helicopter, and the idea here is to select the topological layout of the floor of this structure, as well as design some energy absorbing structures underneath that floor, so that if this helicopter were to make a hard landing, that it has the best crash absorption capability. that becomes a topological type of design problem which has been solved successfully using genetic algorithms. Design of a tilt rotor, which I have shown on the right hand side. This is a multidisciplinary design problem. Structures, aerodynamics, controls, propulsion systems, all of them interact in this design. And some characteristics of this would be designed by decomposition, which requires that you actually have co-evolution of genetic algorithms. I'll say a few more words about that. And then the ability to coordinate what goes on between different subsystems. I'll say a few words about enhancements in GA-based search. A number of adaptive strategies have been proposed for associating significance with bit locations on a string. So if you have very, very long strings, should you use all of those strings as part of the crossover and mutation operation, or can you identify some criticality to certain portions of the string and only work on those? That's the directed crossover and multi-stage search. This also brings me to the subject of immune network modeling. That's a way of actually improving the convergence characteristics of these algorithms. In decomposition-based design, you partition the problem into a number of loosely connected subproblems. You solve these subproblems in parallel, and what that results is a reduced dimensionality, so you have shorter string lengths. But then you have to coordinate the solution between the subproblems because they are in fact still coupled, although weakly. Okay, so this now brings me to the topic of biological immune system. What this is, it actually simulates the schema recognition and adaptation process which is central in biological immune systems. What is it that generates antibodies in our immune system when it's attacked by an antigen, for example? It has been shown that this can be modeled very effectively in genetic algorithms with essentially your bit strings replacing the chromosomal structure. The antibodies are generated when exposed to the presence of antigens, and this task has been modeled in GA. Let me show you how it would be done. Let's say that there are a number of cells in a biological system. The blue line indicates that these are self cells. Here's a invader marked in red. This has to be then tackled or recognized by an antibody, which then attaches itself to that antigen and eventually purges it. So the characteristics of this antibody must be that in biological systems it's a complex protein shape recognition problem. That's here it is a matching of strings, aligning of strings. So you have ones and zeros. Can you actually create a GA-based evolution that does that? So here's an antigens. There are 3 different antigens that I've modeled using zeros and ones. I call this as a generalist antibody. Why is it a generalist? Because it provides maximum coverage to each one of these 3 antigens. You see that this is different from each one of these 3 by exactly 1 digit. So this is the best match that you can get. This is different from 0, 0, 0 because there's a 1 in the middle, 0, 1, 1 because there's a 0 at the end, and 1, 1, 0 because there's a 0 at this end. So this provides the best coverage of this particular antigen. You could also get a specialist antibody. The specialist antibody would be a complete, either a match of this antigen, or it could be a complement of that antigen. So 1, 1, 1, 1, 0, 0, 0, 0, 1 could be a complement of that. Now, how does this play in genetic algorithms? Well, if here's a long antigen and here's an antibody, and let's say I calculate the XOR match score for this, the points at which it's a complement, 1, 0, 1, 0, etc., I've labeled as ones, and you can see that that match score is 13. If I use that as a fitness measure in your traditional genetic algorithms, then in fact your antibodies, you produce a whole bunch of antibodies which are complements of the antigen that you introduce in the population. So you can use the match score therefore as a fitness function, and it is possible to generate both specialist as well as generalist antibodies. Where has this been used? The generalist antibody simulation has been used to improve the convergence characteristics of genetic algorithm-based search, as well as in coordination problem required in decomposition-based design. The specialist antibody has had very specific use in the area of multi-criterion design, and I'll show you very quick examples of each one of these 3. So using the immune network approach to enhance the GA-based convergence, here's how this whole process would work. You come in, you have certain objective and constraint functions designed, you have your population of designs, which I'm just going to label as antibodies. I select the top 3%, 3 to 5% of these antibody pool as antigens, and then using the generalist antibody match function approach, I match each one of these antibodies. I actually randomly select antibodies from this pool using this match function. I then determine the highest scored antibody, add to its match score, and go back and repeat this several times. When this is completed, I have a fitness associated with these designs, which has been modified by this immune network simulation. I now subject this to your typical GA-based operations and repeat this process. The kind of convergence speed up that you get, here's a 25-bar classical trust problem. You can see that there's your convergence pattern of the plain GA approach. We have used things like multi-stage search, directed crossover. They do provide some speed over, but you can see with the immune network based approach, you get down very quickly to where the optimum lies. So while it speeds up the convergence process, I want to put in a word of caution here, the word of caution being that anytime you trade speed of convergence for, if you implement speed of convergence, you are going to lose on an opportunity to try and get to the global optimum. So there's that trade-off that you might actually miss getting to the global optimum because you have sped up the process fairly early in the design strategy. In the area of multi-criterion design, again, here's what multi-criterion design really involves. You're minimizing a vector function f of x consists of several different components. Using a weighted function approach, you take sums of each one of these objectives, construct a scalar quantity, and then try and optimize that scalar quantity. Here's what it looks like. If you were to consider f1 in isolation, the minimum value of f1 is obtained here. If you were to consider f2 in isolation, the minimum value of f2 is there. So this point really in the f1, f2 space represents the ideal solution. But this ideal solution is going to be typically infeasible. The line that separates the feasible domain from the infeasible domain is the Pareto frontier. And on that Pareto frontier, all of your designs are in fact feasible. And you can see the trade-off that if I were to improve on f1, then I lose in f2 in a certain way. So that's the whole concept of the Pareto frontier. And designers would love to actually generate the Pareto frontier vis-a-vis generating a single optimal point, because it really gives the designer then the ability to decide for themselves how they want to trade off designs in the whole process. So in the immune network based approach, you simply designate designs with the best composite fitness as an antigen. This is done for all of the chosen weight combinations, and then you use the immune network simulation to promote convergence of subsets of population around each one of these different weight combinations. This gives you a very nice Pareto frontier that you are able to actually capture. In conjunction with fuzzy modeling, you can also capture non-convex Pareto fronts. This is a weakness for those of you who are involved in design optimization. You recognize this problem immediately, that if you have a non-convex Pareto front, your weighted sum method. Okay. That's not a problem. I think you need a battery for me as well. I'm running out of charge myself, but we'll work through this. So in conjunction with fuzzy modeling, you can actually use this immune network approach to generate non-convex Pareto frontiers. Using just the simple weighted sum method, you would get points that lie the convex part here. You might pick up the point here, but you will miss this entire Pareto frontier. So this is something that a combination of fuzzy immune modeling has been able to overcome. Okay, here's that same design problem that we were looking at earlier, the helicopter rotor blade, 3 subsystems. Now, the important thing to consider here is that when you are doing design in one particular subsystem, you really need the results of analysis from another subsystem as well, because the problems analysis in another subsystem actually does contribute to what's going on in your particular subsystem. So you could use a counter-propagation neural network and use only those subsets of variables that are germane to a particular subproblem, with representations of other variables left out, and still be able to construct an approximation to the output, use that approximation to do design in each of the decoupled subsystems. So that's the very simple idea of using counter-propagation networks with pattern completion capability to actually do decomposition-based design. You can also do coordination through immune network modeling. You could actually have two subproblems, subproblem A and subproblem B. You do evolution in each one of these. You select the best designs in each one of these two disciplines, into each of these subproblems, label them as antigens, and now you do a immune network simulation to generate generalists. So in fact what you're doing is you're averaging what goes on in each one of those subsystems. Use those updated strings to actually continue this process till you get convergence to the desired design. So this allows the process to actually converge as opposed to diverging, that the two subproblems may be going off in different directions altogether. I want to say a few words about parallel GA implementation, coarse grain versus fine grain parallelism. You're essentially dividing the population into a number of subsets. You assign a subset of population to a given processor. You can simultaneously evaluate both the objective function and constraint on that subprocessor. So in effect what you are doing is simultaneous evaluation of the objective function and constraints on different subprocessors. You bring that information back onto a central processor to do your GA operations and then split again. So in this kind of an approach you can get a near linear scaling with the number of processors. The GA operations will still be performed on a single processor. Fine grain parallelism, it was already alluded to this afternoon, where the population is divided into a number of sectors and mating is restricted to within each sector. There is minimal migration allowed between sectors, and there may also be a small overlap between the sectors so that you can get strings from one subsector actually going into the other one. Let me next talk about a paradigm referred to as cellular automata. These are a stylized universe where cellular automata is a stylized universe where space is represented by a discrete grid. So here's a flat plate. I've broken it up into a number of discrete cells. Each cell will contain information about the state of that cell. If you are thinking about just a binary state, the cell could be either a 1 or a 0. You could have a random set of 1s and 0s in each of these grid points. And let's say that you came up with a certain set of rules. The rules say that if all of the west, south, east, and north are 0s, and the center is 0 as well, then the new value of the center value is 0. And similarly, all of the other rules. Now, given some arbitrary state that you start off with, if you applied these rules, you would get to a converged new set of state variables for each of these discrete cells. Here is a very commonly used neighborhood which is referred to a Moore neighborhood, where there are 8 neighbors that are involved in the process. This paradigm has been used in structural analysis. Here's a beam which is discretized into all of these little cells that you see here. The top line actually shows the results that are obtained from elasticity theory using rules that we developed for the cellular automata. Here are the results, and you can see that there is practically no difference between the results that you get from elasticity theory and the cellular automata. Likewise, for a plate with a hole, it's a classical elasticity problem as well. They've also been used in structural design problems. So here's a beam that is subjected to a load. Let's try and find out what is the best structure that is likely to carry this load in an optimal fashion. Is the lightest structure. Through homogenization methods, you get a beam that looks like this. It's just flipped around, so please think of this as pointing the other way, and you can see the cellular automata actually maps the outlines of the beam or of the frame structure that is optimal for carrying this load. Likewise, here's a plate, and you want to carve out the least weight grid that can carry this central load. Results of homogenization shown here, results of a CA-based resizing strategy shown in the adjoining chart. So it has been used in this context as well. This same paradigm can actually become a model for fine-grained parallelism in genetic algorithms. You have a population of candidate designs that are distributed over a spatial grid. Your connected graph is an example of this. The whole concept behind this is that you only invoke the stochastic transformation operators between selected neighbors. So you don't go outside of that. You could shuffle position of candidate designs as an option. A massively parallel implementation is possible. In fact, you could go to as many processors as your population size. This has been applied in problems of multi-criteria design optimization as well as simultaneous analysis and design of structures. Let me just dwell a little bit more into this slide. I'm coming to an end of this presentation. But here's an idea that you have a probabilistic transformation operator, which is simply an expression operator. So here's a Moore neighborhood, 1, 2, 3, 4, 5, 6, 7, 8 neighbors. Here's a central cell. Each one of these has a member of the population sitting there with its genetic makeup. The string, the center site of this has a string, and what we are trying to do is that based on what is available around it, let's update the value at the center. An expression operator is used to do this, and the probability that a string contributes its bit to the express string is computed as shown here, where this worst is the maximum of f in the neighborhood under consideration. If you want to actually, the mutation operation in this is identical to the one that is used in your genetic search. If you want to add state variables dealing with analysis to each of the cell site, so for example, if you're looking at the, if you go back to this particular problem that we talked about, the elasticity problem, if you think of these cells as interconnected by elastic springs, all right, and you want to find out the k value of those elastic springs based on the thickness, that becomes a state variable which is defining the design of the element. So in addition to your GA-based, you could also use the variables corresponding to the analysis as design variables, and these could become additional state variables at the site, in which case when you evolve the state vector, you're simultaneously solving the analysis and the design problem together. So for those of you again who are familiar with optimization algorithms, this is the paradigm that is referred to as SAND, S-A-N-D, or simultaneous analysis and design approaches. Let me close this presentation now by simply stating the obvious, that soft computing algorithms provide remarkable flexibility in the analysis and design of engineering systems. Applications have ranged from optimization to real-time control as well as system modeling approximations. Really the research frontiers in this area are at the interface of algorithm implementation in hardware. I believe that's the next big step that we are going to go through, as well as other physical and natural systems, including biological systems, in fact. So with that, I'd like to stop and see if there are any questions.
What is the reason that we are able to identify the essential features?
If you look at it, what it's telling you, if you trace the path of an input to the output, all right, and you were to carry out what goes on, it is nothing more than a multiplication of these weight matrices. So you can work out that expression. It's the path of important information flow from the input to the output. That's what's being identified by that multiplication operation which I showed you.